go ahead. Have like freaking.
We'll get started in about 2 minutes. Thanks for your patience. All right, thanks everybody for joining in this afternoon. I'll go ahead and get started. This meeting is being recorded, and I will post the recording in the announcements in about a day or so, once I have a chance to get this video out for captioning, or back from captioning, I should say. All right, so I'm gonna go ahead and share my screen. And what you should be seeing now is the course homepage. Could somebody kindly unmute and let me know if that is what you're seeing?
Yes.
Thank you very much. Okay, so just as a reminder, so I did post out an announcement giving an update on the last bonus so that everybody would have the correct information. It was a typo on my part, but we'll talk about that in the coming weeks. I just wanted you to be aware of that in the event you went out and took a look at it so that you have the correct point values for that bonus. So last week when we met, it was midterm week. And so I spent some time answering questions from students about the midterm exam. And that Q&A session is posted in the announcements. just like all videos, I'll post them in the announcement so that you have a chance to take a look at them. So there wasn't any new material last week besides completing the midterm. And that midterm covered everything before Newton's laws that was covered on week 6. So everything up to and including two-dimensional motion was reflected on the midterm exam. And I have not scored the midterm exams at this point. That is on my plate or my to-do list for this week. I'll get that scored and get those scores posted for you this week. In the meantime, if you have gone out and looked at your midterm, I try to be as forthcoming in my comments so that you would know, have some indication regarding the points you might have received or not received for any particular item. However, if what I've shared with you is not sufficient, or if you still have questions remaining, you can visit with me during office hours. Now, for that type of session, I would like to know ahead of time that you're coming to discuss the midterm. That way I can make sure that we have individual one-on-one time in the office hour session and not have other students available, okay? So I have no issue discussing your exam, but I do it on a one-on-one basis, and it has to be done by, during office hours. Just let me know what you'd, when you'd like to drop by and have a chat about it, and we can do that, okay? So we're moving on. This is week 8, and I do apologize. Originally, this Monday was scheduled to be your fall break, but because of the days missed due to the hurricane, fall break was canceled. And so I was a little bit late getting that announcement out to the class. I do apologize, but again, everything in our sessions is recorded. So hopefully if you didn't see my announcement, you're either here or you'll check the announcements and then watch the recording. So this week, the topic that we're going to be looking at is gravitation. And so we have had experience with gravity already. We've been dealing with gravity in terms of the acceleration that it produces, either including air resistance or not including air resistance in our prior materials. We've also looked at gravity from the standpoint of weight, the weight that gravity creates when it pulls on an object. But what we want to do now is look at a more comprehensive view of gravity. And to do that, we need to go back to Newton. If you recall, Newton is very instrumental in this class because not only does he provide the laws of motion, which explain the behavior of forces as they interact with objects. Newton is also credited with helping us to get an understanding of how gravity works as a force when we take into account the masses of the objects involved and the distances between the objects involved. And so that's what we will be looking at tonight. And that's what these objectives relate to. We'll be looking at Newton's Universal Law of Gravitation, and we'll get to see that formula and how the parts of the formula combine to help us understand gravity in a more detailed way. We'll look at the inverse square law concept because that is a key ingredient, if you will, in the law of gravitation. And then we'll look at some examples of how that gravity force actually works on objects from a more detailed perspective, beyond just looking at weight. And then we'll see the connection between the uniform circular motion formulas that we use when we discussed orbit motion. If you recall, the NEO or the LEO and the GEO satellites. And so we'll look at what is the connection between Newton's law of gravitation and these circular motion formulas that relate to orbits. And in the course of looking at that formula, I'll take a look at some examples of how to use the formula. And then while looking at that, we'll explore more deeply the relationship between the variables in that formula. So these are the assignments that you have on your plate for this Saturday, problem set 6 and 7. Now recall, those go back and deal with Newton's laws of motion, problem set 6 and 7, and those both are due Saturday. And then you have a discussion related to gravitation, the topic that we're dealing with tonight, that is also due by Saturday. Just to remind you, information on submitting the problem sets is provided here in the weekly overview. You see the problem set submission instructions. And then if you're having questions, drop a line in the class questions forum, or you can email me or come for office hours. Whatever method you choose to get your question addressed. To help us deal with the topic tonight, I've made available to you chapter 6 in your textbook. Again, that is for you to review. And after you've reviewed it, if you have questions, you can definitely reach out to me. There's some videos. And a NASA website that also deals with gravity. And then, of course, here are my notes, the supplemental notes that I always make available to you. I will also say that in the extra notes folder, there are some really nice examples. And in fact, I'm going to look at a couple of them tonight. And then you can utilize those resources if you want additional materials beyond what I've provided here and the readings and required readings and viewing. So again, here are the objectives for this packet. Those come right out of the objectives in the weekly overview. And so with that, we can go ahead and get into looking at Newton's universal law of gravitation. So maybe you've heard the story about Newton and the apple. Everybody says the apple fell out of the tree and hit him in the head. And when he came to, he said, voila, gravity. Well, it wasn't nearly as simple as that scenario. In fact, it was quite an extensive theoretical thought process that Newton went through to help us understand the behavior of gravity. One thing is for sure, whether it was an apple or something else that fell, on that day when Newton saw that object fall, he asked a very important question that had not been thoroughly addressed up to that point. And that was, why does the apple fall, or why does the object fall? And in the process of trying to answer that why, he relied heavily on the work done by some other key scientists like Kepler. And we'll take a look at some of that information here shortly. But Newton worked out theoretically the relationship that helped to form this universal law of gravitation. And you see here the main idea behind the universal law of gravitation. And that is every particle in the universe attracts every other particle in the universe with the force along the line joining them. So if we pick any two objects in the universe, we can find out the amount of gravitational attraction or pull or force between them by utilizing Newton's universal law of gravitation. And so while Newton wasn't the one who completely worked out the formula, he did figure out some key relationships that are part of the formula. So what he figured out is that if we pick two objects that have mass, for example, little m and big M, the force of attraction or the force of gravity between them is directly related to their masses. So bigger objects or more massive objects have a much larger force of attraction between them. He also figured out that this force of attraction, this gravity between objects, is inversely proportional to the distance squared. And that's one of the key elements of the formula that we call the inverse square law. 1 over the distance between the objects squared. And then 100 years after Newton figured out those two primary relationships, Henry Cavendish came along and experimentally helped us to understand gravity even more by finding the value of this gravitational constant, big G. We'll see the value of big G here shortly. So Newton is given credit for discovering the universal law of gravitation because he figured out the key relationships, and Henry Cavendish came along and refined that relationship to help us have an exact formula. And then if you know anything about gravity, Einstein came along about 100 years after Cavendish and helped us to understand gravity from a different perspective, from the perspective of space-time fabric in his laws dealing with relativity. So, well, let me just spend an additional moment here with this formula because, you know, it does have a great bearing on our everyday experience on planet Earth. We'll see here in a moment that this formula is very, very useful when you move beyond the confines of a planet or a moon, because you don't have to rely on being on that object to determine the distance involved, right? And we'll see how that exactly works. But if you notice, we're finding here in this formula the magnitude of the force between any two objects in the universe. If we know their mass and we know how far apart they are, we can figure out the force of gravity between them. And that force is an attractive force. So little m pulls big M toward it, and big M pulls little m toward it. And we'll talk about how that actually plays out in, you know, kind of real time, if you will. So there are some specific phenomena that are influenced because of this gravitational attraction between objects. For example, if we choose the Earth and the Moon as our two masses, let's say the Moon is little m and the Earth is big M. Well, the gravitational force of attraction between them is what produces the ocean tides that we experience on planet Earth. And that is because, you know, the Earth has a lot of water, which is a fluid. And so as that, you know, pull gets exerted on the Earth's oceans, and because of how they distort, we get this high tide and low tide. And those of you who recall Hurricane Ida, that was one of the things that was most concerning for a great many places, especially near the coast, because if the storm surge coincides with high tide, then you get even more flooding or more surge, if you will, right? So the tides are a direct result of this force of gravitational attraction that was explained and expanded on by Newton and refined by many other scientists after him. Weightlessness is also a phenomena that comes into play when we talk about this force of attraction between objects. In particular, in this case, we're looking at an astronaut in a spaceship that is orbiting the Earth. Well, because that spaceship is free falling around the Earth, and the astronaut inside of the spacecraft is also free falling around the Earth, the net effect there is for the astronaut to feel weightless. However, we know that the astronaut is not weightless. In fact, the weight is almost the same in the space station as it is on the planet Earth, but it's how they feel, okay, the sensation that they experience, okay? And so, you know, we always talk about that scenario of an elevator. So if an elevator is free falling and the person inside the elevator is also free falling, they will experience this weightlessness sensation. But again, neither the elevator nor the passenger is actually weightless. And so when astronauts are in orbit, for example, because of the small acceleration that they experience because of non-gravitational forces, they experience an environment that's referred to as microgravity. Remember, they're not actually weightless, and there is actually gravity in space, but because they're free falling, they feel weightless, except for these small accelerations that are due to things besides gravity. Okay, so that's a common misconception with you know, with a lot of individuals, is that they think you know, once you get out in space, there's no gravity. That is absolutely not true. And in fact, Newton's Universal Law of Gravitation tells us that there's a force of attraction between every object in the universe and every other object in the universe, depending upon their mass and the distance between them, the inverse of the distance between them squared. I mean, it could be very small, but the distance would have to be infinite for it to be zero. Okay, so the question then becomes, you know, what's the natural historical progression of things as it pertains to our understanding of gravity? And so, you know, humans have been curious about the motion of the planets, you know, since we've been humans on the planet. And the ancient Greeks helped to start our understanding by looking at the positions of the planets. But they didn't realize they were planets. They called them wandering stars. And so one of their more important Greek astronomers, Ptolemy, came up with a way of explaining planetary motion that depended on what they called epicycles. But you see, the fallacy of their thought process was that they thought the Earth was in the center of that whole orbital path. Those paths that the planets took all revolved around the Earth, which we know now is completely incorrect. But you know, like everything else with science, you have to start somewhere, right? You can't have a wrong answer. You can't have a right answer until you figure out that some things are wrong in many cases. And then, as I mentioned to you before, Kepler was one of those individuals that was paramount in helping us to revise our understanding of planetary motion. Because Ptolemy got it wrong, Kepler came along and helped to correct that by saying that the sun is actually the center of our solar system, right? Ptolemy had this Earth-centered system, whereas Ptolemy had what we call a heliocentric view of our solar system, there were other scientists who helped to refine this understanding, including Tycho Brahe. So we'll see here in a moment that Kepler was instrumental in this whole process because it was his work that led to Newton's ability to understand more clearly the relationship between mass and distance as it pertained to gravity. See, Kepler, as brilliant as he was in refining our understanding and proposing this heliocentric view of our solar system, as brilliant as he was, there was one major question he could not answer about the planets, and that was why they orbited. He measured a great many things regarding the orbits of the planets. And we'll see that here shortly in terms of his 3 laws of planetary motion. But the main thing that he missed was answering the question why they orbited in the first place. And so that's the question that Newton was able to answer utilizing Kepler's work and the work of others. So while I don't expect you to be an expert at Kepler's laws, in particular, not the first and second law, we'll look at the third law a little bit more closely here momentarily. But the first law, Kepler's first law, looked at the orbits in terms of their shape. Even when we looked at the simulator that showed the orbit of the Earth around the sun, most often we choose a circle for the orbit because that simplifies things, right? That's an easier model, a much easier way to model the motion. But actually, what Kepler showed was that the orbits are actually elliptical, and the sun sits on the focus of that elliptical shaped orbit. And so, he corrected our understanding of those epicycles that Ptolemy proposed. Kepler's second law of planetary motion looks at the area that the planets sweep out as it relates to the time that it takes to complete a certain area of that orbit. So you can see here that in the picture, what they're saying there is that, you know, if we look at the areas A1, A2, and A3, those areas are equal if we make the time intervals that it takes to complete either of them the same. So let's say the time to complete the area A1 is equal to the time to complete A2 is equal to the time to complete A3. Even though if you look at it visually, those areas look like they're very different, right? And so, but if we actually, you know, calculate the amount of each of those areas, we will see that they are in fact equal as long as the time it takes to sweep out each area is equal. And then finally, Kepler's third law. And this is one of the ones that I focus on a little bit more because of its direct relationship to the work that Newton did to help us understand gravity. Okay. And so what this third law looks at is the ratio of the period squared for any two planets, right? If we look at the period, remember, we know what period means because we dealt with it in uniform circular motion. That is the time that it takes to make one complete trip around, right? So if we look at the ratio of the periods squared for any two planets, that is equal to the ratio of their orbit radii cubed, okay? And so, you know, two planets, planet 1 and planet 2, look at the ratio of their periods squared, and that will be equal to the ratio of their radii cubed. So the period squared is related to the radius cubed. And that is an important relationship because if we use Newton's laws of motion and gravitation in combination, we can actually derive out Kepler's law, okay? And so that's important because it shows the consistency between what Kepler proposed and what Newton proposed. And that's how things work in science, right? We aren't going to throw away our old stuff unless we have irrefutable evidence that is wrong, right? Likewise, if we're proposing new stuff, it has to be consistent with the old stuff that we're pretty certain about, right? Now, remember, of course, we know that laws and theories and models can be refined. None of that stuff is set in stone, but there is an important concept of making sure that our new understanding is consistent with and fits our old or current understanding. And that's exactly what happened with Newton's laws and Kepler's laws. They're consistent with one another. Okay, so now that's my supplemental notes, but I'm not done yet because what I want to do is I want to go into the extra notes that I provided you and look at some examples. Okay, so if you recall in the announcements, I provided you with a link to some extra resources. See, way back in September, extra resources, okay? And so if you click on that link, you see there's a folder for every topic that we cover. And here's the one that deals with gravitation. And so when I post the video for tonight, I will make sure that there's a link that takes you directly to this folder, as well as a reminder, you know, of the link that'll take you to the entire larger folder, okay? And so what I want to do now is to take a look at some examples and shed some light on some relationships that, or the relationship between some things we've already studied and this new gravitation stuff. Just to make you aware, these are some great links that deal with gravitation and some additional videos. And this comes right out of the physics classroom. Many of these links will take you directly to the physics classroom. The site has some exceptional explanation regarding gravitation, but it's very wordy. And so rather than me reading it to you, I made it available to you so that you can go and take a look at it. Okay. And so I have a screenshot here that kind of summarizes Newton's universal law of gravitation, which states basically that every object is pulling on every other object in the universe. There's the formula. And we know if we're finding force, the unit is newtons. That's why I have the unit for this force off on the side to remind you that if you're using that formula, you are finding force and you should be getting a unit newtons. One of the things that I did not share with you is the actual value of the gravitation constant. Remember, I said that Newton focused on the masses, M1 and M2, and the distance between them, R squared. And then Cavendish came along and experimentally helped us to understand the value of the proportionality constant, big G. So big G is called the universal gravitation constant. And so constant means what? No matter where you go in the universe, that value is the same. And the value for G is 6.67 times 10 to the minus 11. And then its unit, the units that go along with big G, newtons meters squared per kilogram squared. So Newton times meter squared divided by kilogram squared. So this portion is the unit. This portion is the number. And you can see from the size of that number that that value for big G is extremely small. Now that helps us to understand something when we use the formula. If the masses are very small, then you aren't going to have a very big force between them. Okay. Because big G is such a small number, meaning you have to have some really large objects to overcome that smallness. Okay, and we'll see that when we work out a couple of examples here in a moment. But I also want to remind you about this force is that it obeys what we call an inverse square law. So the size of that force is proportional to that little squiggly looking line, means related to or proportional to. So the amount of attractive force between objects, the amount of gravity between objects is related to 1 over the distance between them squared. And we call that an inverse square law. And if you continue your study of physics, you'll see that there are a number of phenomena that obey what we call an inverse square law. For example, the electric force or the Coulombic force between charges also obeys an inverse square law. So I always tell students, so whether it's small things like electrons or large things like planets, they all obey an inverse square law, 1 over the distance between them squared. Another important thing is to keep clearly in your mind the difference between this universal constant, big G, and our gravitational acceleration, little g. So big G is a constant, and it is the same throughout the entire universe. But little g, on the other hand, relates to a specific location in the universe, and it is not constant. For example, on planet Earth, little g has a size of 9.8 meters per second squared. On the moon, however, little g has a value of only 1.7 meters per second squared. So big G is a constant, little g is not constant, but location dependent. And then I want you to pay attention, because as we work through some examples that I'll take a look at in just a moment, I want you to pay particular attention to the relationship between the weight W that we've already learned about. Remember, the weight of an object is the object's mass times the acceleration due to gravity wherever it's located. So I want you to pay attention to the relationship between the weight W and its gravitational force that I call F of G, okay? And as a reminder, you know, the mass of the objects M1 and M2 are in kilograms, and the distance between the objects is measured in meters, okay? So it's important that you utilize the correct units when you're using that formula, because otherwise you'll be getting some strange values. So the masses have to be in kilograms and the distance has to be in meters when you utilize the gravitation formula, right? So I think with that, we can take a look at some examples, right? So here's the first example that I want to work out with you, okay? And my suggestion to you is that while I am working this, you should pull out your calculator and actually work through this process with me so that you can also confirm your understanding of using the formula. This formula is a little bit more involved than some of the math that we've done before because of the inclusion of exponents in the formula, right? And so to use this, you have to remember the rules of exponents, which you know, you should have learned sometime in your pre-algebra life, right? So let's see if we can use the gravitation formula to complete these two examples. So it says, determine the force of gravitational attraction between the Earth, which has a mass of 5.98 times 10 to the 24 kilograms, and a 70 kilogram physics student, if the student is standing at sea level, which means they're a distance of 6.38 times 10 to the 6 meters from the center of the Earth. Remember, when you use the gravitation formula, what you're measuring as the distance is the distance from center to center, okay? And in this formula, we're using M1 as the Earth, so that's like our big M. And then we're using the 70 kilogram physics student as our M2 or our little m, okay? Because some textbooks will use M1 and M2, and some textbooks will use big M and little m. It really doesn't matter as long as when you substitute correctly and you solve correctly, okay? So we're utilizing big G at 6.673. They carry it out to 3 decimal places. I usually just use 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, okay? And then we're substituting the mass of the Earth, that's 5.98 times 10 to the 24 kilograms, which is our M1, and the mass of the student, 70 kilograms, is our M2. Now notice, in the denominator of the formula, we've placed the distance, 6.38 times 10 to the 6 meters, but we have to square it. And let me also clarify for you. Since we're measuring from center to center, we're measuring from the center of the Earth to the center of the 70 kilogram physics student. But if you think realistically, the distance from the center of the Earth to the student is a good approximation is the radius of the Earth, because you know, the size of the student compared to the size of the Earth is pretty negligible. And so what I like to do when I solve this type of problem is to, I take the numbers and I pull them out and I solve the number parts separately. And then I take the exponents out and I solve that separately. And then I put it back together, okay? So let's see what that looks like. So let's first, and you should be working this with me. Let's take 6.673 times 5.98 times 70, because that's the numbers that are in the numerator. And then we're going to divide it by 6.38 squared, because that's the number in the denominator. And remember, when you square something, you have to square the number and the exponent, okay? So if you take the numbers, you multiply the top numbers and then divide by 6.38 squared, you should get 68.6. So I'll give you just a moment for you to try it out on your calculator. And then if you're not getting that value, maybe I can find a way to share a calculator on the screen and we can do it. But try it on your calculator. Now, if you have one of those fancy calculators, the temptation might be to put the exponents all in with the numbers and everything, you know, just type it all in. The problem with that is if you're not comfortable with how you need to group things, it will not calculate the number or the exponent correctly, okay? So you try it and then tell me what value you're getting. Okay, so for just the number part, is there anyone who is not getting 68.6? Okay, so now we've taken care of the number part. Let's look at the exponents, because we have to also work out the exponents in this problem. So from the numerator, we have 10 to the minus 11 and 10 to the positive 24. In the denominator, excuse me, we have 10 to the 6, but it is being raised to the power 2 or squared. So when you multiply exponents, you have to add them. So 10 to the minus 11 times 10 to the positive 24 gives you 10 to the positive 13. In the denominator, when you raise an exponent to a power, you multiply. So 10 to the 6 squared is 10 to the 12. And now we have 10 to the 13 in the numerator and 10 to the 12 in the denominator. And when you divide exponents, you subtract. So that becomes 10 to the 13 minus 12. And 13 minus 12 is 1. So the final exponent should be 10 raised to the 1 power. So from the number part, we have 68.6. And from the exponent part, we have 10 to the 1. When you multiply that out, that's 68.6 times 10, basically, or 686 newtons. So this 70-kilogram physics student that is standing at sea level on Earth experiences a gravitational attraction of 686 newtons. That means the Earth pulls on the student with 686 newtons of force, and the student pulls back on the Earth with 686 newtons of force. But of course, we know that because the Earth is so much more massive, we don't feel any acceleration. The Earth doesn't, accelerate any because of the student. However, the student experiences an appreciable acceleration because of the Earth. And in fact, that is the gravitational acceleration, 9.8 meters per second squared. And so we can use that to look at the relationship between this gravitational force that is found by using Newton's universal law of gravitation and the formula for weight that we learned a couple of weeks ago. Remember, to get the weight, we take the object's mass times the gravitational acceleration. And so in that particular case, we take 70 kilograms times 9.8 meters per second squared. And if you multiply that out, you will also get 686 newtons. Now, that explains a very important relationship between the force of gravitation and the weight of an object. If you're on the planet, the force that the planet pulls you with is equal to your weight on that planet. So for example, if we wanted to do the same kind of thing for the moon, we would simply replace the mass, take out the mass of the Earth and replace the mass of the moon, which is roughly 7 times 10 to the 22 kilograms. And we would get the force of attraction between the student and the moon if the student were on the moon. Likewise, we could take 70 kilograms, because remember, mass doesn't change. It's the same no matter where you are. But then we take that 70 kilograms and multiply it times 1.7 meters per second squared, because that is the acceleration due to gravity on the moon. And you would see that those two values are also equivalent. So there is a consistency, right? The weight is equal to the force of gravitational attraction between those two objects if, the smaller object is on the planet, right? But let's see what happens in a scenario where we're not on the planet. What if we're not on the planet? So in this particular example, we look at what happens to that force if this 70 kilogram student is riding in an airplane 40,000 feet above the Earth's surface. So they're not on the planet anymore, okay? When they're riding 40,000 feet above the Earth's surface, they're at a distance of 6.39 times 10 to the 6 meters from the center of the Earth. And you might think, okay, 6.38, 6.39, that's not that much of a difference, but it does actually make a difference in the gravitational force. And so if you substitute those new numbers, in particular, the new number for the distance, when you do the math, you get 68.4 for the number part. And again, because the exponents haven't changed, you get 10 to the 1 or 10 for the power, of 10 to be multiplied by. When you do that, you get 684 newtons. So you can see the force of gravitational attraction is no longer 686 newtons. And that's because the student is now off the planet, right? So this is the beauty of using Newton's law of gravitation, because you can find that force of attraction between any two objects, even if that object is no longer on the planet. If the object is on the planet, we can simply do W equals mg. But we can't do W equals mg in this case because the student is not experiencing 9.8 meters per second squared because they're not on the planet. Okay. And so we can see that Newton's universal law of gravitation is of great benefit to us because we can then figure out things like the force of attraction between the Earth and a satellite, or we can figure out the force of attraction between any other planet and a satellite, or we can manipulate that gravitational force to our advantage to create things like a slingshot effect if we want to, fling like a Mars rover into or out of a particular orbit space, right? So understanding gravitation is really, really important because it allows us in many ways to transcend the planet. And so what I want to look at here, and I have it in 2 slides here. I'll look at this one first with the red writing, and then we'll look at this one second. It's a little bit cleaner, but I wanted to kind of highlight some important concepts in this first visual. Okay, so on this past midterm exam, one of the things that you were tasked to do was to figure out the speed and then the centripetal acceleration for a satellite that was orbiting. And you had to use our circular motion formulas to do that. And that is, to find the speed, you had to take 2 pi r over t, where r is the orbit radius and t is the period. And then to find the centripetal acceleration, you had to take that speed squared divided by the orbit radius. And a great many of you did that correctly. Just glancing at some of the exams. I haven't actually scored them, but I kind of peeked at a bit. But now, because we have a more complete picture of orbit motion, we can have an alternate way to calculate this speed and centripetal acceleration. And that is all predicated on the relationship between Newton's laws of motion and Newton's universal law of gravitation. If you recall Newton's second law of motion, it says what? Force equals mass times acceleration. And so we just took that formula and adapted to an object that is experiencing a centripetal acceleration. So we can rewrite Newton's second law as F sub c. Well, the C subscript stands for centripetal, if you recall, is equal to mass times centripetal acceleration. And then we can take that and substitute the value for the centripetal acceleration. So in place of AC in Newton's second law, we can just substitute v squared over r. Okay, so now we have a way of calculating the centripetal force that our object moving in a circular path or circular orbit experiences. But the connector is the fact that this centripetal force is being provided by gravity. Remember, gravity is what's keeping the object in orbit, okay? And so there's an equivalence between the centripetal force, mv squared over r, and the gravitation force, big G, big M times little m divided by r squared. So there's a lot of algebra involved there, and I don't expect you to do any of that. I just wanted you to understand that because orbit motion combines our understanding of circular motion and gravitation, we now have multiple ways of determining the speed and the centripetal acceleration. So in this other visual, which is a little bit clearer because I don't have all the red writing on the slide, you can see that if we want to find out the speed for our satellite or whatever is orbiting, We have two ways to do it. We can use 2 pi r over t, or we can use gravitation by taking the square root of big G times big M divided by r, where big M is the mass of the planet, and r again is the orbit radius. So now, one of the things you should notice from this formula for speed is that the speed of our satellite as it orbits does not depend on the satellite's mass. Remember, in this formula, the mass of the satellite is little m. And in this formula, you don't see little m being represented. And that is because when you do the algebra, it actually cancels out. But that's a very interesting concept. Think about the International Space Station out there orbiting the planet. How fast it goes is not determined by how big it is or its mass. What determines how fast it goes? The mass of the Earth and the orbit radius, which we know is about 4,000 or so miles from the center of the Earth. Likewise, we can determine the centripetal acceleration. Of course, we can take v squared over r, just like you had to do for the midterm exam, or now because we understand Newton's law of gravitation, we can find the centripetal acceleration by using big G times big M, which is the mass of the Earth, divided by the orbit radius squared. And big M doesn't just have to be the Earth. We can use this to find the speed and centripetal acceleration for any planet if we know its mass and we know the distance that the satellite is orbiting from the center of the planet, right? Or the moon, whichever moon we might be talking about. And then the last formula that I have listed there under gravitational motion is Kepler's law. If you recall, the period squared is proportional to the radius cubed, okay? And so that is Kepler's third law. And remember, the importance of that relationship is that it is consistent with Newton's universal law of gravitation. Okay. So that is what I wanted to cover with you tonight. I will stop the share. And then if you have a question, don't hesitate to unmute. I'll be happy to address any questions that you might have on this material. Okay, well, if you don't have any questions for me, I am done with my portion of tonight's material. I will post this video as soon as I can get it a caption for you. Give me a day or two or so to get it out there for you. Remember, if you have questions about your midterm score, once I score it, I know you don't have any questions right now because you haven't seen your scores. But once I score it, if you have questions, don't hesitate to reach out to me. Or if you know you had some particular difficulties with the exam, the content of the exam, you can schedule some time with me and we can take a look at it. Okay? So thanks for joining in tonight. I'll see you back here on next Monday.
Ms. Zena?
Yes.
Yeah, I know I had a bunch of difficulties, so I'm probably gonna have to schedule something with you because I really didn't understand it.
Okay. Well, shoot me an email and we can work out a time to discuss it.
Okay.
Bree and Bega, B-E-G-A. If you have a question for me, please don't hesitate to ask. If not, we're done for tonight.